All right, let me share my screen again. Right, the only real question that came through, for example, 1, for those that have done it, the first part, determine the number of strikes. In the video notes, it was 70, but the answer was actually 78. Right, so that's an ID10T error from my side. Yeah, it was just copying from writing to the video notes that I made a mistake. I haven't changed it in a number of years, so I always expect that query to come up. But disappointed that only 2 or 3 of you found it. Anyway, let's move on to surge arresters. Let's share the screen. Okay. Right. Anybody have any idea what a surge arrestor is? All right, so you've actually got them in your homes, I'm sure. They could be a lightning protector or a voltage surge protector, anything like that. So you've all noticed that when there's lightning, there's a little break or a little interruption in your TV or something, or your lights even. That's due to the coupling of the surge onto equipment, your power lines or whatever. So a surge arrestor is a non-linear device. It's usually made of semiconductor material. And what it does is it caps the voltage and protects your equipment. So we're going to do a little exercise just to show you what's happening. So let's start off with our normal system. Right. This is our device. In your homes, it could be a TV, it could be lights, it could be a washing machine, etc. But that's what we want to protect. So I'm going to start off just by looking at this. Right. If we couple a current source to that line, let's call it inductive, that's going to create an overvoltage. Right. Now that overvoltage, due to that current coming into the line, that could be a direct or indirect lightning strike, that's going to exceed the voltage strength of that device. Right, so we need to protect that somehow. So the obvious way is get rid of that current. If there is no current, there is no overvoltage. Right, so we could short circuit in front of that device. Cool. So there's no current, there's no voltage. However, that also means that you are now shorting your supply. You could put some sort of linear component to direct that current to earth. And that could prevent the overvoltage. However, that still means that we are drawing current from here as well. So I'm just going to draw this here. We're going to use it as a reference. Right. So we know that some sort of resistive component looks something like that. It's linear, so that means at any voltage it's drawing a current. It can direct that current, but it has to be small enough, smaller impedance than the device, so that it can remove the current. What about a diode? That could work. That's a semiconductor. In any case, we've got a device that we call a metal oxide varistor, a surge arrestor, metal oxide arrestor. That's right. So when there's a transient current, when the voltage goes too high, all the current flows down there. Under normal operating conditions, it doesn't affect the current. There's no current flowing down here. So metal oxide varistor has a shape that's kind of like that. Right. So as the voltage increases, the current, the resistance or the impedance of the component doesn't, it drops. So it's not linear. So under normal operating conditions, it's almost like an open circuit. Under transient conditions, high current, high voltage conditions, it becomes a short circuit. Right, so that means any current from that source is going down through here and not going into your device. So surge arrestors, they're very important in installation coordination. We looked at a couple of things of back flashover and shielding failure. So those are different mechanisms that are maybe on the line. You don't necessarily put them very close to any equipment. Well, yeah, you're not really putting surge arrestors there because it's too expensive to put them there.
So to say.
Yeah, you can't see my screen.
You can see your screen. Yeah.
Thanks. All right. So let me start that again. So surge arrestors, they're quite an important part of installation coordination. They're used to protect against unwanted overvoltages. It's a matter of understanding where to put them. So you don't put them on a transmission line because they're expensive and you don't know when it's failed, and it's going to be costly to go and replace those on a transmission line. But you will put them at a substation. So at a substation, you've got your big equipment, such as your transformers, your protection equipment. You've got your substation network, which you want to protect. You don't want that to fry due to a sudden voltage, etc. All right. So the magnitude of overvoltage, this is in the video notes. You can go through it there. If we note it, I can draw it just after this. I can try draw it here. Right, so lightning overvoltages, we found that they're very, very short overvoltages. Remember from your course notes, it's a 1.2 by 50 waveform. So the magnitude of the overvoltage is very high. It can be anywhere all the way up to 5 per unit. And that can be coupled, it can be due to a direct strike or anything like that. So it's a very short impulse. Right, our switching voltages, they're much, much smaller. They sit around the 2.5 per unit, but they are a much longer duration. Temporary overvoltages occur. Those are due to switching on a line or just generators going too high. And finally, your highest operating voltage is just above 1. So those are the overvoltages that a system experiences. The damaging ones are the lightning and switching overvoltages, where you kind of your equipment will survive because it's designed for it, are the temporary overvoltages and higher system voltage. So higher system voltage, we know that's a rating. Temporary overvoltages, if you think of the power frequency withstand in the table, that's kind of what we're talking about there. Let me see if I can draw a curve. So surge arrestor, you wanted to operate for your lightning overvoltages and switching voltages. You want to cap your voltage here. And then you want to allow the normal operating voltages to work. So it must be an open circuit on the right, a short circuit on the left. Let's draw that in. Right, okay. So for the lightning over voltages, switching over voltages, you wanted to conduct all the way to Earth. You also wanted to, it's not an ideal short circuit, it still is an impedance, so that there are characteristics to it. You want to cap the voltage, you saw that characteristic earlier, such that that doesn't exceed the switching impulse withstand level, or BIL, for the lightning over voltages. Sorry, the lightning over voltage impulse withstand level. Or the switching impulse withstand levels for the switching over voltages. There are two types of surge arresters. One is a pure metal oxide varistor. That's the one on the right. The second is a gapped arrestor. So that's a silicon carbide. Right, that's more like a linear component with a gap. If the voltage goes too high at the top, then that gap flashes over. The current is diverted down through the silicon carbide arrestor, and then the current doesn't go through the equipment to be protected. So the current will flow down through the silicon carbide varistor. When the voltage goes low enough again, remember that gap would be air or some sort of insulation gas. It'll go open circuit again when the voltage drops. So that's kind of a self-restoring one. The metal oxide, that's slightly different. It's online the whole time. So it continuously has a very, very, very small current through it. And then when the voltage at the top goes too high, the resistance or the impedance drops completely and the current will flow through it. When the current is gone and the voltage drops, it'll restore itself. Right, I won't attempt to draw the waveforms. It'll be a bit haphazard in this platform, but it will be in the video notes, as well with the voltage current characteristics. Right, it'll be similar to what I tried to draw earlier, just maybe with a bit more detail. Right, so typical surge arrestor characteristics. Right, so let's point out a couple of things before we go any further. Maximum voltage 420 kV. Rated voltage 330 to 360 kV. How does that work? Maximum continuous operating voltage is less than the maximum voltage. That doesn't make sense, does it? Right, does make sense because UM is a three-phase voltage, whereas your rated voltage, your maximum continuous operating voltages, are your phase to earth or line to earth voltages. So you need to divide your phase voltage, your maximum voltage, by √3, or your nominal voltage by √3, to find your continuous operating voltage. There are some characteristics. So temporary overvoltage capability, TOV, it does give some ratings, and you can see that they're slightly higher than the rated voltage or maximum continuous operating voltage. Your maximum residual voltage, and it gives various voltages. So 634 for 0.5 kiloamp, 30 by 60 microsecond waveform. So that's the peak of the over voltage. You can see that it's limited at let's just note that 736, and we're going to go back to the table just now. 36. Right. So if we look at this table, that was for 400 kV system, that surge arrestor gives a power frequency withstand of 630. Lightning impulse withstand is 1425. Right. If we just look at all of those ratings here, they're all below 1425. So our equipment will have a BIL. Our surge arrestor will usually bring our voltage within the limits of that BIL by conducting the current away. The IEC defines a number of ratings for all surge arrestors. And you can see some of the ratings below. It's very much to do with where you install these, how often we have lightning on the system, etc. Right, one important component is the line discharge class. So it may be able to handle a 20 kiloamp. We don't know the we know that the peak current here. But remember, when it's absorbing current, when it's behaving non-linearly, it's going to absorb energy. So each arrestor absorbs energy, and that can cause it to damage or break if it's not defined correctly. All right, I think I'm going to stop there. I would suggest going through your video notes up to the location of surge arrestors. I'll cover that in the next lecture, and then there's two examples one example should be two. All right, one example to go through on the location of surge arrestors. I want to take a bit of time with that one because there's other aspects that influence where to put them, and the equations don't necessarily explain that very well. All right, that's it for today.